In this video, we will discuss torsion and the shear stresses developed due to torsion. In engineering, especially in mechanical engineering, rotational movement is very important. Why? We use shafts to transmit power from a power source with the help of a shaft to the point where it is used. So torsional moments or torques are acting in these shafts and stresses will develop. In torsion, the stress distribution is not uniform. In the middle, no stress, no strain. The shear stress increases linearly with the distance from the center, and on the surface we will have our maximum shear stress. If we know our maximum shear stress on the surface and we like to calculate the shear stress for a given point P, which has a distance rho, so we can use the formula and find the shear stress in P. So what about the value of the shear stress? Let's take the maximum. So this formula tells me the following. Your maximum shear stress on the surface depends on the torque you apply, on the radius, and on the J value, which is the polar moment of inertia. Polar moment of inertia represents the resistance of the sections against torsion. Well, the torsion formula is torque times the radius over polar moment of inertia, and for a section, polar moment of inertia is the resistance to being distorted. So we have to use this simple formula to calculate the polar moment of inertia, and using tubular shaft is very common. Why? Because in torsion only outer layers carry high stresses, so when you use a tubular shaft, well, the resistance to being distorted will not change too much, but your weight will be smaller. An example how to use this simple formula. The torque is given. It's acting on a shaft with 10 millimeter radius. All you have to do is to calculate the moment of inertia for 10 millimeters and put the numerical values into the formula. You see here Newton, meter and millimeter is used. Well, you can make the life easier when you take everything in millimeters, then your result will be in Newton per millimeter squares, which is actually megapascals. Okay, here we have a problem, a shaft, diameter 40 millimeter, and there are different gears on the shaft, and torques are acting in different direction. Well, in this direction 200 plus 500, in the other direction 300 and 400. Well, as you see, the shaft is in equilibrium. I need to find the internal torques in different regions. Let's take region 1, 2, and 3, and for the first region, you make a cut, take the left side, it will look like this, and for equilibrium, well, the torque should be 300 and in the shown direction. What about the sine? So for the sine, you take your right hand and direct your thumb in the normal of the section. your other fingers will be like this. Okay, so this is your positive direction. So this moment is negative. Well, second region, cut here, free body diagram, 100, again in the negative direction. Last, this time you take the right part. As you see, your torque is 400. What about the side? This time the normal of the section is directed like this, and if you take again your right hand and your thumbs will show the positive directions, so my torque is 400. As a result, the maximum value is in region 3 and is 400 Newton meters. I take my simple formula, my torque, my radius, and the J in polar moment of inertia. All units are in newtons and meters, so the result will be in pascals, which is Newton per meter square, and you can convert it into megapascal, and the result will be 31.85. Another problem. Here we have a nut and we are trying to tighten the nut with a force of 300 newtons. The moment arm is given. The critical section is tubular. The internal and the external diameter is given. Find the stresses on the inner and outer surfaces. Well, the first thing I have to do is to calculate the torque in this section. Well, it is force times the moment arm, and in Newton millimeters I have my torque value. Next, polar moment of inertia. We know that the formula is okay, and this time I put my radius values in millimeters and the result is also in millimeters. Next step is to use the formula. Well, for the other surface, torque, inertia, polar moment of inertia, radius. That's my result. So in this case, Newton and millimeter is used. The result is Newton per millimeter square, which is directly megapascals. For the inner surface, the radius changes. It is 10 millimeters, and here we have 23. So on the external diameter, I have a stress 35. Internal surface, I have a stress 23. When we apply torque to a shaft, then the shaft will be twisted. Now we're going to discuss the twist angle. The angle of twist depends on the applied torque, the length of the shaft, the polar moment of inertia, which is the resistance of the shaft against torsion, and the shear modulus, which gives the rigidity of the shaft's material. We remember that G is the constant, the shear modulus, which relates the shear stress to the shear strain in the elastic region. Well, the Hooke's law in the axial region, in the axial loading, looks like this. For shear, our formula is tau equals to G times gamma. Here, sigma equals to E times epsilon. Okay, this is my formula. And the signs we have already discussed. You always put your thumb in the direction of the normal of the section, and this will be your positive, and Here the direction of the normal looks like this. The positive direction can be found with the other fingers. A simple problem. Well, we have a shaft with a diameter of 14 millimeter, and the shaft's materials has a shear modulus of 80 gigapascals. Find the twist angle in point A. The other end, which is point E, is fixed, and the shaft can freely rotate in this bearing B. Again, we have 1, 2, 3 regions. So in each region, different torques are acting, so they will be also differently twisted. The first we do is we cut in these regions, and my diagram, and first calculate the polar moment of inertia. The radius is the same everywhere, and this is the value of the polar moment of inertia. So next thing is to calculate the theta values for the three regions. We remember the formula. It looks like this. This value and this value are the same for all three regions. Only torques and the lengths are different. So we have to calculate the thetas and add them together. So this is how we do it. For the first region, plus 150, length is 0.4 meters. This is my J and this is my G value. And for the second, well, the direction changes. I have negative 130. For the third region, negative 170. If you do the calculation, the results will be in radians. In all our formulas, we get our angles, or we put our angles into the formulas with the unit radians. You can of course convert radians into degrees. How do you do it? You divide it by pi and multiply with 180, and then you get your result as an angle. Shafts are used for power transmission. If you have a power source, let's take an electrical motor, and here you have a gear. The angular speed is given, so the power transmitted can be calculated with the help of this formula. Power is equal torque times the angular speed. It looks like the formula we remember for linear movement. As you see, force times the speed was the power formula. Here we have this formula. Remember that omega here is in radians per second. In daily life and in industry, the rotation speed is usually given in frequencies. Using radians per second is not very common, so you have to convert this rounds per minute into radians per second for using this formula. How do you do it? Well, if you have 100 rounds per minute divided by 60, you will get rounds per second. If you multiply it with 2 pi, which is the radians per one rotation, so you will get your radians per second unit conversion. With the help of this formula, we can determine the torque if we know the power and the angular speed. So if you know the torque, you can choose a shaft, and the formula is on the shaft surface, the shear stress is T times R over J, and this should not exceed the allowed shear stress for the material. Well, you can write this formula in this form, and as you see, here you have J over R. J includes also R, so when you know the ratio of torque divided by the allowed shear stress, you can calculate G over R, and this ratio contains only R values, so you can determine the necessary R value for the shaft. An example, a solid shaft is used to transmit a power of 3750. Rotation speed is 175 RPM. Determine the required diameter of the shaft. For the shaft material, the allowed shear stress is 100 megapascals. First, start with 175 RPM divided by 60, that's rounds per second, multiplied with 2 pi, you will get radians per second, and this will be your omega. Okay, this is what we have done, 18.33 radians per second. Next, well, we have our formula. This is my power, and this is the omega I have calculated. I can determine the torque value which is acting on this shaft. If we know the torque value and the allowed shear stress for the shaft material, I can calculate R over J. You know that in this J we have also R, and so if you do the arrangement, you can find this formula R equals to 2 times the torque divided by pi times tau allowed, and as you see, put the numerical values and you get the radius, and the diameter of the shaft should be minimum 22 millimeter, so that we do not get higher shear stresses than 100 on the surface of the shaft. Another problem, an engine power is 200 kilowatts and rotation speed is given. Here the shaft's dimensions are given. The outer diameter is 100, the wall thickness is 20, the outer diameter is 100, so it means that the inner diameter should be 60. Find the maximum shear stress and the rotation angle or twist angle of the part, which is 2 meters. Well, the twist angle of this part is asked, G is given. Well, first we do take RPM, convert into radians per second and find omega. Next, this is my external diameter, internal diameter. Put the radius values in meters and get the moment of inertia in meters. Next, put the values of P and omega, and what you get over here, what is Newton meter per second, Joule per second or Newton meter per second, and when you do the calculation, this is your torque. Next, you know the torque. You know the outer radius, and this is your J, which you have already calculated. The torque here, this is your radius, and that's your polar moment of inertia. And the Mach maximum shear stress on the surface of this 2-meter shaft is 9.31 megapascals. Next, twist angle. The twist angle, the formula is given like this. I know everything. Torque, length, J, and the shear modulus. Everything is in Newton and meter, and so they will all cancel. What you get is in radians, 0.00464. Multiply it with 180 divided by pi, and if you like, you can find also the result in degrees. Stress concentration in torsion. When you have a shaft and the section size changes in these areas, we will have stress concentration like in axial loading or bending or so on. Similar effects for clutches or for keys, and for all these geometrical changes, there will be a stress concentration graph. Well, this graph is an example for dimensional changes, and with the help of this graph, you can calculate a stress concentration factor K. How do you do it? Well, you have your capital D, small d, and this radius on the fillet. Well, what you have to do is calculate these two ratios, take these ratios, go up and to the left, and find the K factor for torsion. A problem, a shaft is given, and the torques acting on the shafts and the radius values are also given, and in the fillet the junction radius is 6 millimeter. First, what I have to do is to find the K value. For this, I know that the smallest section size is over here. This will be the point where the torque is maximum. For this, I cut here and get a free body diagram. In this region, the torque is 30 Newton meters. Well, I can calculate with the formula very easily the torque in region 1. But this is valid for the region, but for the fillet, I need to consider the stress concentration and I need to calculate a K value. For this purpose, I calculate the values d over d, which is 40 divided by 22, and the r over d value, which is 6 divided by 40, that is 0.15. So, with the help of the graph I have shown in the previous slide, you can find that the K is 1.5. Next, well, all I need to do is do the calculation for region 1, the torque, the radius, and the J value, and multiply it with K for the stress concentration point, which is 1.5, and the result will be 3.1 Newton millimeter or megapascals. Okay, in this video, we have discussed the torsional loading and the stresses and the twist angles due to torsional loadings, and also solved some problems. Thank you for listening.